What are the thermodynamic limits of cooling using coefficient of performance? Imagine trying to cool a room with the least amount of energy possible. How efficient can that really be? That question takes us into the heart of thermodynamics and how it limits what we can achieve with cooling systems. The key idea here is the coefficient of performance, or COP. It tells us how well a cooling device uses energy to remove heat from a space. If a refrigerator has a high COP, it means it removes more heat for each unit of work or energy it consumes. But no matter how clever the design, there are fundamental limits set by the laws of thermodynamics. The second law of thermodynamics says that heat naturally flows from hot to cold, and we need to do work to reverse that flow for cooling. The maximum efficiency of this process is described by the Carnot cycle, which is an ideal, perfectly reversible cycle. It's like the gold standard for efficiency, even though real systems can never reach it. The maximum theoretical COP for cooling is calculated by taking the temperature of the cold space and the temperature of the surroundings, both in Kelvin. The formula is the cold temperature divided by the difference between the hot and cold temperatures. So, if the cold space is at 20 degrees Celsius and the surroundings are at 30 degrees Celsius, you convert these to Kelvin and plug them into the formula. The closer these temperatures are, the higher the maximum COP. That means cooling a space to a temperature just a little below the environment is much more efficient than cooling it to a very low temperature. This limit is important because it shows that, as you try to cool something to very low temperatures, the COP drops. It takes more work to remove each unit of heat, making the process less efficient. For example, cooling a refrigerator to freezing temperatures in a hot climate will always be less efficient than in a cooler environment. In real life, actual cooling systems perform below this ideal because of irreversibilities like friction, heat losses, and imperfect gases. These factors make the COP lower than the Carnot limit. Still, understanding this maximum helps engineers design better systems and set realistic expectations. So, the thermodynamic limits of cooling using the coefficient of performance are all about the temperature difference between what you want to cool and the environment. The smaller that difference, the better the potential efficiency. But no matter what, the Carnot cycle gives us the ultimate benchmark. It reminds us that while we can improve our systems, we can never surpass the fundamental laws that govern energy and heat.